So you may have noticed before we started with my update on the classroom page, I also updated the my SolBridge page. If not, you can see it right now. This is going to be mainly about linear programming. The two linear programming questions that I had originally put on the schedule for last week, but they take a long time, so we didn't have time to get through them. Please don't draw on the screen. Thank you. We'll do a few matrix addition and subtraction questions first. Not too many of them because it's really not that hard. You just kind of directly add or subtract. So a little bit of time on that, and then we'll move over to the linear programming questions. I will have more practice questions about transposing matrices, scalar multiplication, matrix multiplication, but we'll finish up that stuff in class on Monday or Tuesday next week, depending on which section you're in. So then the workshop that we'll have next week Thursday, then we'll do a whole bunch of matrix specific practice. But today is still primarily about linear programming. So I hope that's useful for everyone who is here. These are the specific questions. So I have 3 planned out from matrix addition. So not from our main textbook, as I've mentioned. We are using this other book for the matrix operations. Our main textbook has matrix elimination, but not addition, multiplication, that stuff. So these 3 questions here will not take very long. And then maximization question about houses and a minimization question about feeding pigs, pig nutrition is the topic. Okay, let's get on with these. Right, matrix addition. I have these matrices here, the 6 that we see up here in the top right, and then 3 specific operations that we can do on them. All right, so let's just, before we jump into those, it's been a little bit since maybe we've done matrix addition. Tell me first what we need to do in order to do matrix addition or subtraction, and then tell me what the conditions are that we need to check before we do it.
First, we need to find the rows and columns.
Find the rows and columns. Can you be a little more?
In terms of the order of the components on the rows and columns.
Okay. So the first operation is telling us to do matrix C plus matrix D, and we have C here and D here. So let's write these out. So C is 1, 5, 8, 92, 12, 6. All right, and D is 10, 14. So what about these 2? What about the rows? What about the columns?
3 rows and 2 columns.
Okay, you're telling me the size of the result?
I mean, we add the first component of the first.
Okay, so you're telling me what the size will be of the resulting matrix. So the first one here, matrix C, is a 3 by 2 matrix. Let's do this in a different color. 3 by 2, because we can see it has 1, 2, 3 rows, 1, 2 columns. The second matrix we're adding, D, same thing, 1, 2, 3 rows, 2 columns. So also a 3x2 matrix. So our results will also be a 3x2 matrix. Okay, so that's part of it. That's the condition. What's the actual operation we're doing?
Let's just add the numbers in the same place.
Okay, in the same positions. So you're adding the ones in the same positions. That's the key part here. So our result is a 3x2 matrix, and we're just matching up the positions. So let's do this color. So here we have first position. So row 1, column row 1, column 1, and we take row 1, column 2 in the second matrix, and then we just add them. So 1 plus 10, that's
11.
11. And we do the same thing for all of the positions. Just find the matching position on the other side, add them together, and that's it. 5 plus 14 is 19. Okay, tell me what the rest of the values are here. Next row.
8, 7. It's a 14.
14.
Yep.
15.
15 here. Next one.
94.
Okay, last row.
17 and 67.
And 67. Some of you guys have echo there.
Thank you.
Yeah. Okay. If you have echo, if you have two people in the same room, if two people who are joining here listening together, that can make echo. One person should turn off their mic and their speakers. If you're in the same room and you're getting echo like that, Zoom should be smart enough to stop that from happening. Okay, so just match up the positions, add the matching positions. That part is really straightforward. The only condition here is that the dimensions must be the same. So both of these are a 3x2 matrix. So the result is also a 3x2 matrix. What happens if my two matrices that I want to add or subtract are not the same dimensions? What do we do?
We transpose them.
Okay, let's say matrix C and matrix B. B transpose is still a 2x2 matrix, and C is still a 3x2. If we transpose that, we would get a 2x3 matrix.
Then it will be like impossible.
Okay, so we don't just do a transpose for fun. If the question specifically says what is C transpose plus something else, then we look at C transpose. If it doesn't tell us to look at C transpose, we don't do it. We only do it if the question specifically states it. So you can't just, it's not a thing you can add in on your own. It's a different it's a different matrix. They're not equal. C and C transpose are not equal. So we can't just switch them back and forth freely. Someone's microphone is on. Okay, so the condition, they must be the same dimensions. If they are not, we stop. That's the answer. So if they are not exactly the same dimensions, we just don't do the operation, and we say that the operation is undefined. So I'll write this one out here. This was C plus D equals the result. Let's do the next one. B minus E. So matrix, let's write this up here. B minus E, which is 2, 14, 22, 6, and minus B, 6, 12, 14, and 5. What's our result?
-4.
2/2.
It will be 4,
-4,
2,
2,
2,
8, 1.
and 1. Okay, that's it. We're just subtracting. Nothing surprising, nothing tricky here. The last one, D minus B.
Impossible, we stop.
Okay, why does it not work?
Because D is 3/2 system and B is 2/2 system.
Okay, so we have different dimensions, so we cannot add them. 61 minus, let's write this up here, 2, 14, 22, and 6. This is undefined. So that's our result. This is an undefined operation. There are conditions about doing matrix addition or subtraction. This doesn't fulfill those conditions. So we just stop. We say we can't do it. So this is an undefined operation. Okay, that's all the practice for the matrix stuff. Again, matrix addition subtraction is not too complicated. So I don't think we need to do a lot of practice on this. Does anyone have questions about these at all before we move over?
Yes, I have a question.
Okay,
As I read it before, if the rows of the first matrix, no, if the columns of the first matrix and the rows of the second.
that's matrix multiplication. That's a different operation with totally different rules, totally different way of doing it, totally different results. Matrix addition, adding, and matrix multiplication are completely separate concepts. Don't get them mixed up. So the columns of the first one, rows of the second one, that's only for matrix multiplication. That does not hold for matrix addition. So matrix addition is the simple one. It works exactly like you'd expect. Must be same sizes, just match up the same positions and add them together. That thing, matrix multiplication, is weird, has strange rules and strange results. We're going to talk all about that on Tuesday, Monday or Tuesday next week. But that's, don't get that confused with this. Don't think that those rules apply here or that these rules apply there. You got to separate them.
Yes, I get it. Thank you.
Okay, you're welcome. All right. Any other questions? Okay. All right, back to linear programming, our favorite topic. Okay, so the same slides that I've shown you lots of times about the vocabulary and how to do it. I will assume that we are mostly okay with all of that, and we just want some practice. So this is the one from last time. Skip over this. This is the next one here. Okay, so take some time to read it and then tell me what you, after I will ask, and you can tell me what you notice about this and how you think we should start. So just read, understand as much as you can. All right, are we sort of ready? Okay, let's talk about the problem and see what we notice. I know I always said identify variables first, but even before that, is this a maximize or minimize problem?
Maximize
Maximization.
Maximize what?
profit.
Profits. Okay, so nice to just get that out of the way. We're trying to maximize some kind of profit here. Before we say variables specifically, what kinds of things do you notice? What seem like the key terms here that we should be caring about?
2-bedroom houses and 4-bedroom houses.
Okay, so there's two kinds of things that we're building: 2-bedroom houses, 4-bedroom houses. Oh, let's highlight here: 2-bedroom, 4-bedroom. What else do you notice?
The constraint on the number of cars and residents.
Okay, so 2-bedroom, 4-bedroom constraints. It looks like we will have something about cars, also total number of people.
And also the land area or something like that.
Okay, so something about the land. All right, any other key things that we notice?
And also the profit per type of house.
Okay, so we have profit, and profit is coming from something about the houses. One more key thing I notice.
Percentage of the total site, which is covered by communal facilities.
Okay, so this 40% of the land for this this kind of construction project is going to be used for communal facilities. So basically not houses. 40% not available for houses. All right, let's do the formal stuff now and build all this out and see if we can turn this all into some math. All right, our variables first. What makes sense as variables here?
How about T and F?
T and F, okay. And what will they represent?
T is for numbers of 2-bedroom houses built.
Houses built, okay. And F?
The same thing, but for the 4-bedroom houses.
Okay, so T for 2 and F for 4. Okay, so we have two variables. Can we talk about our constraints in terms of these variables? Let's try to do that. Asadbek, your microphone is on. We can hear something ringing.
Sorry.
All right, constraints. Okay, so we think that land, cars, people are our constraints. Let's see if we can use the variables to make an actual inequality for each of those. So actually land, yes, that's going to be a little harder. Let's start with some easy ones first. Cars. Can we make one for this?
1.2 T plus 0.5 F.
1.2 T plus 1.5 F
Is less than or equal to 120.
less than or equal to 120. Okay, let's just, I'll highlight in the text here where we see this. So the people or families who are living in these 2-bedroom houses will have on average, or will own on average 1.2 cars. And families living in these larger 4-bedroom houses will own on average 1.5 cars. So 1.2 times T 1.5 times f. And we have said that there cannot be more than unsuitable for more than 120. So 120 is okay. Less than 120 is okay, but more than that is not. So that seems like it works with our constraint here. Okay, next one, people. We have a people constraints.
2t
2t
plus 5 5f
5f
is less than or equal to 250.
less than or equal to 250. Okay, so 2-bedroom houses average 4 people, sorry, 2 people, and 4-bedroom houses average 5 people. There's the 2 and the 5, and total number of residents should not exceed 250. So there we go. Okay, land. Let's do the variable part of the land first, and then we'll see that the other part we got to do a little more work. So what's
60
go ahead. Yeah.
I'm sorry, Professor. 60 t
Okay, so 60t
plus 300 f
300f. So these
is less or
4-bedroom
equal
houses.
to
Yeah.
is less or equal to
Something. So the number that they gave us, the amount of land available to build houses is 20,000 square meters. So that seems like it's the right number,
but
except we have this 40%. So how can we, what can we do with that?
20,000 minus 20,000 in brackets. Can we do it like 20,000 minus 20,000 multiplied by 0.4?
Yes, what's the reciprocal of 40%? What's the other, what's the complement of that?
Multiplied by 100, right?
Why not just 20,000 multiplied by 0.6?
That's what I was thinking. So
Hi, sorry.
40% is not available, then 60% is available. So 60% of 20,000, what is that number?
12,000.
12,000. Okay. So to get our constants, the actual constraint number for the land one, we had to do a little more work, and we had to consider this 40%. So that's the extra little challenge to this one, but the rest of it was not too hard. Just erase. Oh, no. Nope. Little box that lets me erase that has weird boundaries on it. There. Okay, so constraints, looks like it worked. Our variables have let us make inequalities for each of the constraints, and they seem accurate. So now let's just try out our
Profit.
objective here. So our objective, which we said is maximize profits. And what is our equation for this?
15,000.
15, yep.
15,000 t plus 50,000 f.
50,000 f. Okay. So that's how we maximize our profit, or that's how we calculate our profit, and we want that to be as large as possible while staying inside all of these constraints. I haven't written it here because at this point, I'm sure we understand it, but we also have this t must be greater than or equal to 0, f must be greater than or equal to 0, because it doesn't make, you can't build a negative number of houses. So the problem will not tell us that directly. We just have to add in our kind of common sense here and figure that out. All right, do we have everything? Are we maybe missing something? What do you think?
I don't think so.
We're good? Okay.
Uh,
Yeah. Someone else?
we need to find intercept.
Sorry, say that one more time.
We need to find intercept.
Okay, so we'll do we'll do that when we're ready to actually do the graphing. For now, I was just asking if we have the setup part. Did we pull all the information needed from the question itself? So
yeah, how about expectation? Like how much profit should they expect if they did so?
That's what the objective is telling us, right? So given all of this, we can figure out here you should be building this many 2-person houses, this many 4-person houses, and when you do so, you will reach exactly this profit. So I think you might be thinking of the cases that we had 2 weeks ago, I think, where we said, here's a target profit, can we meet it? This is the more advanced version of that question. They're not asking us, here's our target profit, can we meet it? They're saying, tell us the maximum possible. So we're maximizing it for them. Okay. So basically, the first part is saying here, what should T be and what should F be to maximize the profit? And then how much profit should they expect if they do so? Just that's the actual profit. What is the maximum profit? And this little last part here about which constraints are slack, that's something to solve, but it's not information that will help us do the solving. So we'll come back to that at the very end. All right, so next slide. I have everything here, just for a note, same information that you guys gave me. Sorry, non-negativity I wrote as X and Y. That should be T and F, but the rest is T and F here. Okay, so here's a graph, which is very conveniently already made to be the right size that we need. Surprise, surprise. So let's graph these. So we need I have our T on the horizontal, sort of like our X value, and then our F as our vertical axis here. So let's figure out what each of these are. What are the 2 intercepts for land?
200
200
and 40.
and 40. Okay, and for people?
125 and 50.
And the last one?
100 and 24. No, 240.
That's going to be smaller than 120. We're dividing by a number larger than 1, so our number should be getting smaller.
40.
60. Wait,
Divided-
80.
Okay, 80. 80.
80.
Dividing by 2 would give us 60. So 120
48.
divided by 1.5, 3 over 2, that's 120 times 2 over 3. So that's 40 times 2, that's 80. All right, so 80 there. Let's put that stuff on our graph, and then we will look at the objective function afterward. Sorry, one more time. I'm going to cheat and look ahead of my slide just to do everything in the same color I had it before, or to do everything in the same colors. All right, so we'll do land in red and people in blue and cars in purple. Grabbing tools. All right, so T 200 and F of 40. Asadbek, I think your microphone's on again. 125, 50, and 180. Okay, so we have these three here, it looks like. So I'm thinking that I maybe messed up colors. Yeah, sorry, I reversed the colors of what I had on the other slide. Doesn't matter. We probably won't need to look at it. Okay, so we have these inequalities here, and we want to figure out if we are working above these, below these, in between these somehow. What does our shaded area look like?
Below.
Below all of them?
Yes.
Okay, so yes, we are less than or equal. This is also a maximization problem. Maximization, typically we're just sort of shading down in the bottom left corner and then not anything above. Just quick side note, that's not always the case. We could very much have a linear programming question with a maximal constraint and a minimal constraint, like this must be less than or equal to this, but this other thing must be greater than or equal to that some other thing. So this little triangle here in the middle could be our feasible region, or maybe this shape between these three, below the purple, above the blue, above the red, that could be a feasible region for an optimization problem like this. So it's not always the case that you're all below or all above. Just read the inequality signs carefully. But in this case, we're right. We are below all of these. So we should identify our corners. What do we have?
Red corner on F for which 50.
Okay, so red and F here. Let's do these in green. Red and F.
Intersection of red and blue corner lines.
Okay, red and blue.
Blue and purple lines. And 100 purple line.
Okay, purple and our T-intercept there. All right, so we have 4 corners and it will be one of these 4. Let's label these A, B, C, and D. Sorry, question?
Yes, I have a question. How do we find which area we should use? Like this pink area, feasible region? Or what?
Yeah, the feasible region, that's based on the inequalities that we have here. So let's look at the first one for land. So we talked about this when we talked about how to graph an inequality. Was this last week? Feels like it was longer ago. Yeah, I think it was just last week. There's a preview question about this as well. So graphing an inequality, we have 60t plus 300f less than or equal to 12,000. So that gave us the red line. So either we're shading everything above the red line or everything below the red line. Which one is it? Well, the easiest way to do this is to just substitute in the value 0, 0 for the origin. You can substitute any point you want, but if it's 0, it's going to be really easy. So 60 times 0 plus 300 times 0 less than or equal to 12,000. So that gives us 0 is less than or equal to 12,000. Then we look at this statement here. 0 is less than or equal to 12,000. Is this a true statement or is this a false statement?
True.
This is a true statement. So the point we were testing down here in the corner, the origin, must be included. So those were the coordinates 0, 0 that we had here. So if we test a point and the statement is true, then that point is inside the inequality. So that means that we are shading below the red line. That point and everything else that's on the same side of that line, all of this, everything below the red line satisfies the red inequality here. So everything below it. So that's how we do it for one of them. And then we just do that for all three of them. So the blue one and the purple one. And then we look at the area that matches all three of them at the same time. So based on our inequalities less than or equal, we must be below the red line and below the blue line and below the purple line all at the same time. This pink area here is the only area that satisfies all three of the inequalities together, not just one of them at a time. So that's the feasible region. You're just reading the signs on your inequalities and shading the appropriate side.
But if the statement was false, then we will shade up the side, right?
That's
That is
correct.
not
Right.
included,
Right. So
zero.
if this statement were false, if it were 0 is greater than or equal to 12,000, if it's a false statement, then that would mean the point that we tested, in this case, 0, 0, that point and everything else on the same side must not be included, and therefore it must be the other side. If you really want, you could also just pick some random point on the other side and test that one as well to be absolutely certain, but that's not really necessary. So if it's a false statement, you're shading everything on the other side of it.
Okay, thank you, Professor.
You're welcome. All right. There. Okay, so we have our 4 corners here, A, B, C, D. One of those 4 will be the solution to this, the highest profit. So we have our profits equation here, 15,000 T plus 50,000 S. And we need to pick a constant for this while I plug in my little writing tablet here. So we want a constant that looks like that will give us easy math and also be reasonably close to the shape, the feasible region that we already have here. Can someone suggest a constant for us to try out?
300,000, maybe.
300,000. Okay. Sorry, 1 second. I'm just gonna edit the slide and move these numbers over a little bit so we have some space to write. Profit and this one there.
Oh, I think it's too big.
There's definitely a problem with it. I'm gonna write it out. We're gonna do it anyways, and then we'll see what the problem is. So 300,000. If we did that one, what would our t-intercept be?
20.
20. Seeing the problem already. What about our f-intercept?
6.
6.
It's too small.
That is much, much too small. I'll put that on here just for fun so we can see it. 20 and 6, so like there. So that tiny little thing down in the corner. Based on that, can you tell which of the corners is going to be the best one? It's too small. We want to think bigger. So the thing here is we will look at our intercepts here, and this is a maximization problem. So whatever our T and F intercepts are, they should be close to, but a little bigger than whatever the other intercepts are, kind of the average of the other intercepts. Doesn't have to be bigger than all of them, but bigger, a little bigger than most of them, or sort of like at least halfway. So instead of, I can think of a very easy adjustment here. Instead of 300,000, can we do a different number?
3 million, Professor.
Okay, so just multiply everything by 10. And we will get 260. That might be a little big, but it's definitely going to be a lot closer. So let's try that. 200 for T and 60 for F. Okay, so that's that green line there. That's telling us something. What do we, are there any points here that we can eliminate based on that result?
D and A.
D.
D, and we're saying A as well. A and C both look pretty, they seem like they're about the same distance to me. So at least D, we can be pretty confident that we can get rid of that one. Let's be extra cautious here. Instead of, I know I told you that you can just slide things over by using a ruler. So we could just line a ruler up on our green line and just sort of slide it down if we're using a piece of paper. I have these, line tools, so I could just drag the line down. It'd be very easy, but let's do it with our constants. Can someone tell me a new constant that's not much below, a little below this? We've already drawn 2 of these, so we can use that to help us. We have way down here in the bottom left corner, this was 300,000, and then the second one here was 3 million. You can see the distance between them. You know how much closer we need to get. So give me another number that seems like it could work.
Uh, 2,500,000 maybe.
2,500,000. Okay. That is not going to divide evenly with the 15,000. I can think of a number that's pretty close to that, but will divide evenly. Instead of 2,500,000, I'm thinking a number just a little smaller.
700,000.
That's a little bigger. I think we need to.
750,000, right?
I'm thinking 2.4 million, 2,400,000. Your other numbers, you could use those as well. I want the math to be easy here. So we are scaling down by 80%. So multiplying by 4/5 here. So my 200 intercepts, what will this become? $200 times 80% of 200.
160.
Sorry, one more time.
Is it 160?
160. Okay. And what about 60? What's our new intercept there? 80% of 60.
48.
That's 48. Okay, good. So I'm just doing this by scaling. If you did want to recalculate the 2.4 million, 15,000, that will also work. All right, so new intercepts. There we go. 160 and 48. 48. That's 45, 47.5, a little more into 48. Okay, so there's our new line. I'll label that for us. But just from looking at this, it seems like we are doing pretty well here. Can anyone tell me what they think the best corner is?
B.
Okay, looks like B. I agree. I'm just trying to find space to write these in where it's not going to get in the way for anything else. 3 million, 2.4 million. We could label our other little one here, 300,000. Okay, so B looks like it's closest. Again, we can think this distance between point B and this green line here, and we can compare with this distance between point C and the green line and A and the green line. They're pretty similar. So there's not going to be a major profit, a huge profit distance between, or difference between A and B and C, but B will be a little bit higher. There's no reason to leave money on the table. If we can earn a little more, then go for it. So point B, we can identify as our best corner here. Where is point B? What are the exact location? What is the exact location of that?
It is 50T, 30F.
Okay, we're saying this is 50, 30. How confident are you in that number?
I can substitute and check.
Okay, let's do that. We shouldn't always trust our graph. We may have made a small mistake. When I look at this, it looks like we're pretty close to those, but to me, the intersection looks like it's a little bit off from the 30-50 intersection. So this is the red and blue lines. So we have these two, 60T plus 300F is equal because we're on the line here, 12,000, and then we have 2T and 5F is equal to 250. Okay, let's do elimination. So do we want to eliminate the T or the F here?
T.
T, okay, so what are we multiplying it by?
30.
All right, so people, 30 times our people. Inequality, so 30 times 2 is 60, that matches, and we're going to be subtracting here. 30 times 5, what will that be?
150.
Okay, and then 30 times 250.
360,000.
757.
Yeah, 750,000. We got to do the times 3 as well there. So 0T and 150F, and this will turn into 4,500. So F is equal to what?
30.
30. Okay, so we've confirmed it, and then the other one, from this point, T is not very hard to figure out, but let's just do that quickly here. So 2 times T plus 5 times F, which is 30, is equal to 250 here. So then 2T will be equal to 100. So T is equal to 50. Okay, so we weren't totally sure about our graph. It's a little off. That's probably just me drawing the lines not perfectly, or maybe because the lines are a little extra thick or something. But 30 and 50 looks like it's our solution here. So, or sorry, that's where the solution is. So we 30, 50 here. And our actual profits. They've asked us to calculate the profit here. So let's do that. I'll go up here in the corner. So 15,000 times T, which is 50 plus 50,000 times 30. And what do we get there? What is our profit at this location?
750,000 plus what's that? 100.
1,500,000.
Yeah.
Okay.
2,000,000.
So
2,250,000.
Yeah.
1.5 million here. One more zero. So then our number is 2,250,000. So 2.25 million. Okay. So there is the actual profit that we would get. So here's how we get that profits, 50 and 30. That's the maximum. And then also here's the actual maximum. That's the actual number they can expect. Okay, and the question asked us about slack constraints. Today's class, today or yesterday, depending on your section, I know it was the first time that we saw that, but let's see if we can remember. So let's get rid of these objective lines here to help us. Which constraints are tight? Which constraint or constraints are tight and which ones are slack?
Land and people constraints are tight and cars are slack, Professor.
Okay, how do we know that?
Because I substituted the the result we got, and to land and people matched it, the kind of answer, but cars didn't. There was surplus.
Okay, so we can do that. We can take this point here and we can substitute that into our land inequality, substitute it into our people inequality. It should be exactly equal to the right side because point B is on those lines. It's at the very edge of those inequalities. Remember, it's the red line or anything below, blue line or anything below. We are on those lines. Even just one step past them is not a valid solution. We are outside of our feasible region. So we've hit exactly the maximum. So if we substitute this into land and people, it should be exactly 12,000, exactly 250. So if you want to do a confirming process and like confirm your results, that's how you can confirm it. If you're confident in your result, we don't need to do that substituting because we trust our graph and we only need to go back into the other one, whichever thing, or there could be more constraints, whichever ones are not at that point of intersection where our best corner is. So from point B to the purple line, there's a gap. We can see there's a gap right there. That much is slack. So at point B, how many cars do we believe there will be in this neighborhood?
105.
105. Okay, so that cars here would be 1.2 times 50 plus 1.5 times 30. We work that out and it's 105. Okay. Is that right? Yes, 60 and 45. So we can have at most 120 cars available, but based on our calculations on the averages and everything, then we think we will only have 105 cars. So the cars constraint is slack, and it is slack by exactly 15. We think that we will have 15 fewer cars than what the upper limit is. So can we do anything with this? Sometimes we can, sometimes we can't. So if you are a company building a new neighborhood of houses, and we had this limit on how many cars, but we think we will be under this limit. can you think of any business thing to earn more money using this slack, this extra condition that we have here?
Maybe we can decrease the area for cars and change it into the land area for houses.
Okay. Two problems with that. I would say first, decreasing area for cars. If it's a neighborhood, we have like roads, and they're probably not building like a parking lot or anything. It's just people will just park at their own house. So I don't know that there's a way to reduce area for cars that would like reduce access roads or something. Like you still need to have a road going to each of the houses and everything. Also, if we change more land for cars aren't taking up land, they're taking up road area. But even if they were taking up land, we can't build more houses because we don't have any, or we're at our people constraint anyways. So we can't build more houses because we'd have too many people and we'd be over that limit. Anyone else, entrepreneur who can think of ways to earn money from this?
Like especially the cars would take a garage to keep them. And it is mainly equal to, maybe it's a parking slot, 2 by 2 meters place. And that place can be a garage. And if in that case, people can use for another purpose, or we can leave them, because not only people will be living there, even some guests can also come to the town. When the guests come, they can use those free slots for their cars.
Okay, so the parking, again, is, I guess, depends on, you know, what neighborhoods typically look like in this country or that country. Where I'm from, it's usually people would just park like at their house. They have just a little spot in front of their own house. But yeah, maybe we say, okay, that's not a huge spare, that's not a huge difference, and we want to just leave it open for guests to come. Or maybe we tell people like, okay, your house is allowed to have this many cars, but if you go over this, you can buy a permit from us to let you have 1 extra car parked in front of your house or something, because we have some slack and we can just kind of sell the extra available somehow. I don't know, whatever. Sometimes we can do something with the slack, sometimes we can't, depends on your actual real world context and I guess how creative you are. Okay, so that's this problem. 3 constraints. We figured out slack and tight constraints as well. We had one little extra thing with having to reduce the land by 60%. So there's not really hard math there. We just had to read the question carefully and make sure we understood it. Any questions about this one before we go on to our next one?
Professor, just a quick note. If I'm not mistaken, we a little bit confused the label for cars. It was supposed to be 1.5 F, and with the profit also 50,000.
Sorry, can you say that again? So cars for the
1.5
variable.
F. We made it as like the
Variable,
labels.
Professor.
Variables.
Yes, S. Okay, that was it was a different example, and I was adjusting the numbers, and I forgot to. Yeah. All right, let me fix those right now. We did some good work on this. I have another example, a minimization problem that we can do. Why don't we just take a 5-minute break right now, a breather, and then we'll come back and we'll work on the minimization problem. So I'll fix my little mistakes in the slides. You guys can go stretch your legs, go to the bathroom or something, and then we will resume at 8:37 in 5 minutes. All right, it's 8:37, so we can resume. Hope everyone's ready. So from our previous example, we'll go ahead to the next one. As I mentioned before, this is example 2.20 from that same textbook that all the other ones are from. This is a minimization problem. It's a little more straightforward than the other ones. Then like the last two examples that we've looked at have been some fairly large maximization problems. This one's pretty straightforward, but still, if you always do it in one direction and not the other one, not do minimization, it can be a little confusing. So take a moment and just read this and think about it and see if you can identify variables, how many constraints, what's the inequality, and the profit function, or sorry, our objective function. So take some time and read it and see what you can identify. Okay, it's been about 2 minutes. So let's see, gave you a little more time to think. Hopefully you were able to identify a bit more of the problem here. Variables, what do we think are the variables?
S and V.
Okay, tell me what they're going to represent.
S will be representing the type of additive.
Okay, so the S for the Sealy swine, V for Vita, so Siska, whatever. Okay, so C whatever and Vita. And what about them? What exactly about them?
The percentage of content.
Those are part of the inequalities. Those are part of the constraints. The variables themselves are going to be a more sort of fundamental thing.
The amount of additives they will be representing.
Measured with what?
Kilos, right?
Okay, so kilograms.
Right.
So 1 kilogram units of this one, and then 1 kilogram units of the other one. Okay. All right, so constraints. What are the constraints that we have?
20 S.
But first, give me the category first. What are we representing? Then give me the inequality.
I'm sorry.
That's all right.
Cost. Protein content.
Okay.
60 S plus 90 V.
90B
is less or equal to 36.
36. Why? I see the 36. Why 60 and why 90?
Actually, it should be 0.6 and 0.9. I'm sorry.
There we go. So remember, we write percentages as like 60 and 90 and such. Just for convenience, the real number here is 0.6 and 0.9. So 0.6 and 0.9. And
For vitamin content,
yeah, vitamins.
0.4 S
Mhm.
plus 0.1 V
Mhm.
is less or equal to 10.
Less than or equal to 10. Okay. I agree with a lot of this. There's one part with each of these I think we need to change.
I think maybe it's greater or equal than,
Okay, tell me why.
because we shouldn't give less protein or vitamin to those pigs.
The pigs, yes. The pigs, we want the pigs to stay healthy, so greater than or equal. If we give them a little too much protein or a little too much vitamin, they'll be fine. They're not going to die. But if we don't give them enough food, they're not going to grow healthy. They won't grow big enough, or they'll die early or whatever. So over that amount, not a problem. If I don't know, animals, if we're like way over the amount, maybe something bad will happen. But for a little bit over, not an issue. Under the amount, definitely a problem. So greater than or equal to. Okay, good. And our objective here. What is our objective?
Minimize costs.
Okay, so minimize costs. And how are we calculating cost?
20S plus 15V.
Plus 15V. Okay, good. So everything seems like it's set up and it is working. So just making sure our units all kind of line up here. So 36, so 36 1 kilogram units. And also our cost is in terms of per kilogram, per 1 kilogram unit. So that all works out with the variables. We have to make sure we're representing the same concept in the same units. We had the one question last week where we had minutes versus hours. We had to do some conversion there to make sure we're measuring it in the same way. Okay, so that's the setup. Fairly simple problem here, and I've just typed this out a little more cleanly for us. All right, so looks like we are ready to graph, which we can do here. All right, so our two inequalities, yes, I'm going to do blue there, start with pink. So we have S and we have V, and I've chosen to put S on the horizontal axis and V on the vertical axis. So tell me what our constraints will be for S and V here for protein.
60.
Okay.
And 40.
And 40. So we're dividing by a number that's less than 1. So the number should be getting bigger. Just a little quick review here. So dividing by 6/10. So 36 times 10/6. So 6 times 10, 60. All right. For vitamins, what are vitamin? What are the two constraints?
25
Mhm.
and 100.
And 100. Okay. Looks like we're ready to graph those. So we'll do those first. Blue, thick line, there we go. 60 and 40. And then 25 and 100, like this. Okay. Are we shading above or below these lines, or in
Above.
between? Above. Okay, so these are both greater than or equal to, just repeating what I said for the earlier one. Get rid of that. If we took either one of these, so say 0.6s plus 0.9v greater than or equal to 36. We could test any point we want, but just test the point 0. So 0.6 times 0 for S and for 0 for V. So obviously the whole left side is going to turn into 0. 0 is greater than or equal to 36. False statement. So our origin down here is not included. Therefore, everything on the other side of both of these lines must be what we're shading in. For the one we just looked at was the blue one. So everything above the blue line, everything above the red line. But when we put those together, it's this area here. And then extending off into infinity, all of this space as well. But I'm not going to shade all that in because it just looks messy. How many corners do we have on our shape here, on our region?
3.
3. Tell me where they are.
100.
A little more detail.
Red line on the V.
Okay, so red
The
line
corner.
and the V axis here. So 100 on the V axis. Yep. And
Intersection of red and blue lines,
red and blue.
and blue line on T.
S
60.
axis down here.
Sorry, S.
So A, B, and C, we can label these 3. One of these is the, remember, minimize. We want the lowest possible cost. Actually, I forgot. I was thinking of this as a maximize. So I need my labels on the other side here. So we have space. Okay, so we have those 3. We have a cost equation here. 20 and 15. Tell me a constant that will make the math easy for us.
For 450.
450, okay, not the most obvious choice, but it should work. What are the two intercepts here? The S doesn't quite, we'll stick with this and see what happens, but there would have been easier choices. What's the S intercept?
It will be.
If you can't do it in your head right away, you've chosen a number that's unnecessarily difficult. There definitely would have been easier choices. Sorry, tell me the S intercept again.
22.45.
0.5.
0.5. That should be a clean 0.5. And what about for the V?
30.
30.
Okay. Before we even graph this, can you tell me another constant that would work out a little more cleanly than that?
600.
600. Okay. And what would the intercepts be for that?
30 and 40.
30 and 40. Okay. So looking down at our graph, we can see the kind of scale that we're working with. So 30 on S and 40 for V. Would that give us an ISO cost line that's going to work? It looks like it. So 30 and 40, it's a little bit lower than what we have kind of the middle or the average for the other constraints here. So that seems like it'll work. The 22.5, I kind of don't like that because the more precise I can be with my graph, the less guesswork I'm doing. So my grid gives me these 10, 20, 30, 40 very cleanly. So nice whole numbers means just less guesswork. Green line here, 30 and 40 like this. Okay, so we have our one ISO cost line. Tell me some corners that are not going to be the solution.
A and C.
Yeah, so this one's not too hard. So A, really far away. I know we can't directly see what the perpendicular line would be because it's sort of off our graph, off in this direction. Same for C. But we can tell that it's getting further away. Look at the distance at point B here, and then think of another perpendicular line here, another line here. It's clearly getting further away. As we move from B to C, it's getting further away, so we don't want to be going in that direction. And same thing for A, if we just sort of imagine perpendicular lines, keep extending them like this. They're getting further, so A will be further away than B. So not too hard to just sort of put that information together and understand that B is going to be our best choice here. Okay, where is B? What are the exact coordinates? Can we read it off our graph?
No.
Yeah, so this one, it looks pretty clearly like it's not lining up exactly. It's not 30, it's not 20, 30, it's some other point. So we need to do a little bit of work to figure that out. All right, so we have our two, this will be a two equation system, two equations, two unknowns. So let's do this here in blue. So we have our protein one and we have our vitamin one. So let's do elimination. And if we eliminate, what should we be multiplying each of these by to be able to eliminate? Or sorry, which variable do we want to eliminate? Let's decide that.
V.
Want to do V, okay. So then we're multiplying vitamin by 9. All right, so 0.6s plus 0.9v is equal to, because we are on the constraint line, 36, and then times 9. So 3.6s plus 0.9v is equal to 90. Just make sure 10, 9, 4, looks like we have that right. We are subtracting because we have the same sign on the V's. So we will get negative 3s, and here on the right, what are we getting?
Negative 54.
Negative 54. So S is equal to
18.
18. Okay. And let's take this back into our vitamin one. So 0.4s plus 0.1 times 18 is equal to 10. See if you can work this out faster than me. 0.4s plus 1.8 is equal to 10.
Professor, shouldn't we be adding, I mean, substituting 18 to the 0.4?
For S, yes. Okay, thank you. I could see something was wrong there. I didn't immediately see what. 0.4 times 18. Okay, and plus 0.1 V. Just make sure I'm looking at the right things here. Okay. 0.4 times 18. What's that number?
7.2.
All right, 7.2 plus 0.1 V is equal to 10. 0.1 V is equal to 2.8. So V is equal to
28.
28. So point B looks like it is 28, 18.
Is that the opposite, Professor?
Did I? Sorry. Wow. I must be tired. Let's try that again. 18 and 28. There we go. Okay, so there's the location, and we can figure out the actual cost here. So our minimized cost. Right this way. 20 times 18 plus 15 times 28. And what does this equal?
700.
Sorry, I couldn't hear you.
780.
780 whole thing. Okay, so if we trust our numbers, then we have this right. This would be 14, 28, 420, and this one would be 360. Looks right, 780. So there is our minimum cost. So we should buy 18 kilograms of nutrient thing S. Always happens. I forget to turn that off. 1 second. Okay, so 18 kilograms of thing S, whatever that is, I forgot the name already, and 28 kilograms of thing V, whatever that was called. So there's how much we should be buying or how much we should be using of each to get these nutrients and the minimum possible cost, and that actual cost is I don't remember the original, was it dollars or pounds or euros or it was pounds? Okay, thank you. So 780 pounds. There's the problem here. So do we have anything slack in this solution?
No.
No, because we only have 2 constraints and our intersection point is at the meeting of those 2 constraints. We could have something slack if point C was the solution, then red would be slack vitamins. And if A was the solution, then blue protein would be slack. If we had something slack in this scenario, could we do anything about it? Could we use that information in some way? Remember, this is about 2 different kinds of nutrient mixes that we're adding to some pig's food.
Wouldn't that mean the pigs will have a deficit of one of the nutrients?
A surplus, no. So I'm
Oh,
saying, so C or A, let's imagine, like in this case, it isn't, but if they were the best solution, and if, you know, they met all the requirements and everything for the problem, then in this case, that would mean that there's more, we're feeding, let's say it's point C. That means that we're feeding them more vitamins than is necessary. But it's mixed in whatever this nutrient, whatever, it's just like, I don't know, some big, like a bucket or something you just dump in, or like you open a bag and dump it in. Like the vitamins, they're not just sitting there loose. We can't just pick them out. So it's already mixed in. So you can't really do anything with it. Like maybe the pigs eat it and their bodies don't use the vitamin, and then it, you know, comes out of them later, and then you like sift that and try to like chemically separate the, like, no, basically. In this problem, it's just ends up being waste. We can't really do anything about it. So sometimes knowing slack is useful. The case we had in class yesterday or today about the extra worker, we can do something about that. We can fire that or lay them off or retrain them or do something else with that. But you're just putting extra things in like nutrients and food. We can't do anything about that. So sometimes it's helpful, sometimes it's not. Anyways, this is our solution. Does anyone have questions about this example? Okay, so I'll give just a little wrap up here, some tips, and then we'll finish. So linear programming. You know, the way I've been teaching you to do this, like this is the way that it's taught in like all the textbooks and whatever online material you want to find. This is like the standard way of thinking about it. At least for a 2-variable problem. If we have more than 2 variables, things get harder. But for just 2 variables, this is the typical way. But still, lots of students still kind of have some confusion about it. So if that's you, my tips here: quick graphing, keep it in standard form, find the 2 intercepts the way that we've been doing. That's just really quick, especially when you're doing the objective functions. You can just really easily pick a new constant, try it out, see what, and if it's too big, too small, you can just easily adjust, and you can graph a whole bunch of those ISO whatever lines, ISO profit, ISO cost, just really quickly. Won't take you a lot of extra time to do another one if you do the standard form and the 2 intercepts thing. So that's quick, but we have been doing that every time. Choosing a good constant for the objective functions. Just make up a number. If you have a calculator, then whatever, you just type it into the calculator. On our tests, you won't be able to do that. So pick look at the coefficients and just find something with really easy math that will divide nicely into the constant where the coefficients will divide nicely into the constants. Just with our standard form thing and finding the intercepts, that method, constant divided by one of the coefficients. Just, you don't need to make the math harder for yourself. Choose an easy number, multiply probably the easiest way. Take the 2 coefficients, multiply them together, and then the intercepts kind of almost directly come from that. Whatever, multiply them together, make that your constant. If it's too small, then just increase it like times 10 or times 100 or divided by 10 or something. Or if it's just a little off, then just double or half or something. So multiply the two constants together, and then just scale up or down as needed. Sorry, multiply the two coefficients together to make the constant. Scale up and down as needed, times 2, times 5, times 10, easy numbers. That's probably the simplest way of doing it. Before you even graph, you know if you have a good constant if your intercepts are kind of a little above or a little below sort of the middle point of the constraint intercepts. If it's a maximization problem, they should be a little above because you want a line that's a little above your feasible region. If it's a minimization problem, you want one where it's a little below that middle area because you want to be below the feasible region. If it's a weird problem with a weird kind of feasible region, then just sort of get it nearby and see what it looks like and then adjust from there as needed. If we do need to adjust, if you're on paper, just get your ruler and slide it over. The important thing is the slope, not the constant. So constants just slide things up and down. Don't rotate your ruler, that totally changes things, but just keeping it at the same angle, sliding up and down a little bit will definitely help. Verify with algebra afterward if you are highly relying on that. I don't know what rulers look like in other countries, but Korean rulers, you can see it's clear and there's a grid behind this. So I can just use the grid here to line up with some other line with whatever line and then draw a new line. And I can be very certain I'm matching the same angle. So these are really handy to have. You are welcome to have and use a ruler on our exam. All the rulers I saw in Canada were always like just solid. They didn't have this grid on them. So if that's you and you want to buy a Korean ruler, very handy. Right. If you're on a computer like I am, or when I was doing these, you can just draw a line and then just drag the line side to side and see where it's going to touch. Those are the big things. After a few years of doing these linear programming questions with students, I sort of realized that there's another sort of quick way of finding what corner will be the best one just by looking at the slopes and not having to do any graphing. If you're curious, you can hang around and I'll explain that just after we formally end here. It's going to be kind of confusing. So if the methods we've been going through so far are sort of confusing for you, you might not want to try to learn that as well. It'll get extra weird. But if this is fairly comfortable for you and you want to see a faster way, then just hang around and I'll show you that. Okay, so those are my tips about how to do these linear programming questions. Otherwise, just remember where is it? This basic process. It'll get you there. I know there are a lot of steps and extra little things to remember, but with enough practice, you'll be able to do these as well. Does anyone have questions they would like to ask? Okay, so we got through them. We got through the problems that we wanted to. This was our second workshop about linear programming. We'll do a whole bunch of stuff about matrices in the next one on Thursday next week. Thanks for coming. Thanks for listening, everyone. If you want to see that last little thing, then just hang around. Otherwise, enjoy the rest of your day and your weekend, and I'll see you next week.
Thank you, Professor.
Thank you, Professor.